In this video, we're going to look at how to integrate routed firewalls into the VXLAN fabric. This way we can see like how you connect a firewall in order to do something like bring internet in, maybe a default route, or DMZ networks, so networks that are going to be behind the firewall, how we would set that up and how we would route to them and provide the connectivity. So we're going to look at about 4 or so examples. They're going to be a little bit different, get a little bit more complex each time, but none of them are too bad. And just to show just a few different of the kind of the common ways of how it works. So the first one that we'll look at is called, I'm calling it single firewall, single VTEP, which just means we have one firewall, not an HA pair, just a single firewall, and is behind a single switch in the fabric, or VTEP. And in short, the way that this works is through a static route. So we put a static route on the VTEP, or the switch. It points to the protected network, and then we just redistribute that static route to the rest of the fabric. So that tells the fabric how to get to that protected network. And we do the same for the default route. We make a static default route, redistribute it in BGP. That lets the fabric know to go to this VTEP if it wants to get internet access. So let's look at how this would work for this example. So here's the diagram that we've been working with so far. It's the same one, but I've converted Nexus 5. It is now, it's not an external border gateway anymore. It's just a normal node. And so I had to bring, the VRFs over here, the layer 3 VNI. So it's doing what 3 and 4 are doing, which is processing hosts. And sometimes this will be called a service node just because it has a firewall hanging off of it. And we're also going to assume that this is just one tenant. So we're just going to zoom in on one tenant here, which is tenant 1, which is what we've been using, tenant 1, or the orange tenant. So the color coding is a little different, just to point out things related to, firewall. So the green is going to be the inside network, and then this gray is the DMZ network. And so I have 2 diagrams. The left one is the physical diagram. So this is what we'd be looking at when we configure the devices. And then the right one is the logical diagram, what we would look at if we're maybe doing design work or just high level, how's this network get to this one. And so we have 10.0.0.0, it's the internal network, would be this cloud here. And then this router just means the layer 3 VNI fabric routing. It's just being routed by the fabric. So if 10.0.0.0 wants to talk to VLAN 9, for example, it's just done by the fabric, like normal layer 3 routing that we've looked at. And so the inside network here is VLAN 9, and the DMZ is VLAN 192. And then I just have the firewall outside connected like a point-to-point to a router here that's simulating the internet. So I do have this configured already, just because I don't want the video to be too long, but I'll show the key configuration components and show how it works and that it works. And so the key configuration kind of here would be this right here, which is on Nexus 5. And you can see there's the routes that we put. So 192.168.1 is the DMZ. And then we're pointing it to 10.9.0.1, which is the gig 00. That's the IP address that's right here. Then we're saying for the default route, also go to the inside interface. And then we have a route map that permits everything. We go into the BGP, and then we redistribute our static routes. And then we use the route map, which permits everything. So this is just saying every single static route we put, that'll be redistributed. You can lock that down differently if you need to by changing the route map. And then default information originate has to be there in order for this default route to take effect. So this is going to be how that works. So in other words, if Nexus 3 wants to get to the internet, it will know about the default route, and it'll have a next hop set to Nexus 5 because of this redistribution here. And other thing I wanted to point out was the difference between the traffic flow if we were to look at the physical diagram and the logical diagram. So in other words, if we think about the physical diagram, PC1 wants to talk to PC2. PC1 would route up here, and then it would go to the firewall. It would go to the inside interface. The firewall would route it to the DMZ, and then the DMZ is gonna send it to PC2. So that looks different, you know. That's how it will kind of physically work. And then logically, if we were to think about, you know, from this perspective, it's just going to go here inside the firewall, DMZ. And the way back would be sort of symmetrical. So here, the way back would be here. And then the way back PC2, we change colors. PC2 starts here. It has to go to its gateway, which is the DMZ. And then the firewall switches it or routes it to the inside, which then sends it to PC, back to PC1. So it looks a little crazy. But let's get to see how it works in the lab. So here we have the same diagrams, and Nexus 5 I had to convert, I converted back to a normal node. And so in other words, it has the VRFs and everything. Let's look at the VRF. So here's the two routes. It's really the only thing that's added here is these two routes. So here, Nexus 5 is saying if I want to get to the internet or if I want to get to this DMZ, I'm going to send traffic to the next hop, which is this gig 00 interface. So I have a VLAN 9 to show the VLAN 9 here. Show an interface VLAN 9. This only exists on Nexus 5, and the point of it is just to get to the inside interface of the firewall. It's a /24, but there's only two things in there. There's 10.902, which is Nexus 5, and then 10.901 is this gig 00 interface. So here's the ASA I'm using, and here's gig 00. There's the inside interface. So there's the inside, and this is just an access port in VLAN 9. So that's just an access port in VLAN 9. And then the DMZ, this is just an access port in VLAN 192, which is the DMZ VLAN. Now, VLAN 192 exists on 4 and 5. It has to exist on 4 because of PC2, and then it has to exist on 5 to provide the connectivity here. And now the default gateway for VLAN 192, though, is this DMZ interface here, the gig 02, which is 192.168.1.1. In other words, there is no Anycast gateway for the DMZ. And that's like that on purpose because we need to force the traffic to go through the firewall. So on Nexus 4, we don't have a VLAN 192 interface VLAN 192. We only have the VLAN. We only have VLAN 192, and it's in Ethernet 3. I think that's not even part of the thing, but it's on E13, which is this down-facing interface. So that's kind of how this one works. So if we go to Nexus 3, and if PC1 wants to talk to PC4, let's just look at the routing table. And so here we're looking for this right here. That's the DMZ. It knows to get there, it needs to set the next, or, send the traffic to 5. That's the next hop. And the reason that it has this route again is because of our redistribution. When we redistributed it, it just now BGP passed it to 1 and 2, which passed it to 3. And then the next hop, just from the normal BGP process, gets set to the loopback of whatever, or the source of whatever you're using, which in our case is the loopback. And that's how Nexus 3 knows. So let's go to PC1 and let's see, make sure this works. And so we can see that it can talk. And let's see if we can go also to the internet. So let's go back to Nexus 3. And did we see the internet route? Here's the internet route. And it has the same next hop. So if we go to PC1, and I just have on the internet router, I just have a loopback 8 with that IP address just to make sure we can get to it. So again, the key configuration are these static routes in the VRF. And then they're being redistributed into BGP. That way, the redistribution has this effect here. It passes them on and it sets the next hop to Nexus 5. And that way, when Nexus 5 receives it, it does its own internal lookup. And then it would send it to 10.9.01. And then, of course, the firewall has to have some routes pointing back, some basic routes, however you want to do that. I just have a few static routes here. So I'm just pointing everything to the outside, and then anything that's 10.0.0 gets pointed back in. I think that's all. That's enough for this one. So let's move on to the second scenario here. And this is the second scenario we'll look at here, where we have again, it's a single firewall connected to a single switch, but we're gonna do eBGP instead of a static route. So this is gonna work almost the same as far as traffic flow, pretty much the same, but it's a little more dynamic from the Nexus side at least. We won't have to put static routes there. We'll actually move those static routes down to the firewall, and we will, learn them over that eBGP connection. So let's look at this topology. So here's it's the same thing almost, except for we're running eBGP here between, this interface and then this interface on the firewall. So before, this was a layer 2 port, like this was in an access VLAN 9. Here, I've went in to the Nexus and said no switch port. I gave it an IP address, and then I gave this one an IP address. Like on the physical interface again, I just made it something different. I think I did 10.255.7, and did 5 right here, and then 1 right here. So I used the /24, just no reason. But the point is, after we gave these IPs, we set an eBGP session up. That way, anything here, any DMZ on the firewall, we can have it be sent to Nexus 5. And then likewise, then it'll be sent to the route reflectors, which will reflect it down to 3, 4, and whatever else. So here's the logical diagram. The point here is, here's the fabric. And then on Nexus 5, we have these IPs that get us to the inside and outside. So let's look at some of the key configurations. So the key changes, besides that, I didn't putting the IP here, but once that's there, really all that's needed on Nexus 5 is setting a BGP session up inside the VRF. Now note that this interface here is inside the VRF. And then in BGP, we go into this subsection, which tells Nexus 5, I want to look in this tenant VRF, all the interfaces in that VRF, and establish a neighbor with 7.1, which is the firewall. And it's an eBGP session. On the firewall is where we have the majority of the changes. So we have a static route, that's the route to the internet. And then we have a prefix list that matches it, and then a route map that calls the prefix list. Here I'm just controlling, because later I'm going to do redistribute static routes, and I'll only want to catch this default route. So, and then we go into the router BGP configuration on the ASA, and we activate the IPv4 unicast family. Here's where we set the neighbor up. Redistribute connected will have the ASA advertise the DMZ because it's directly connected. Redistribute static, and then we specify the route map filter, which is just the default route. That combined with default information originate is needed for the default route as well. And so a Nexus 5 is where really the change is going to be. E13. There we have it. And again, this is in the VRF. That way, whenever we do our BGP connection, here we're telling it to create a neighbor here, and it knows to use this routing table. And then on the ASA is where most of the changes are. Show run router on here. So redistribute connected, that would advertise the DMZ. And then this route map and this default information originate would get the default route. So if we go to Nexus 3, show IP route VRF, tenant 1, there's our default route. And the next hop is Nexus 5. And then the DMZ, next hop, Nexus 5. So if we test the connectivity, so PC1 is talking to PC2. And again, this is going to be, the traffic pattern is going to be similar to what it was before. In other words, when PC1 wants to talk to 2, it sends its packet out here, and it has to go to the inside. It comes to Nexus 5. Nexus 5 does a lookup, and it knows about the DMZ because of the EGP connection it has on the inside interface, which means it sends it to the inside. Once it gets to the firewall routes it over to this DMZ subnet, and then it has to, kind of bridge it over, or in this case, kind of VXLAN encapsulate it to 4, which then sends it to 2. So that's the traffic flow. That's the same as it was before. So I'm just showing that because it looks, it's going through the firewall is the point. And then we'll test the internet connectivity. So that works too. Again, PC1 is going to go from 3 to 5 to the inside to the outside, and then it's just going to come back up. It's not going to use the DMZ for this case. Okay, so this is similar to the first one. It's more dynamic from Nexus 5. And, if you had a bunch of DMZ subnets here off the firewall, the good part would be that, the redistribute connected would get all that. And if you have some static routes and you want to control them, just put them in this prefix list that's wrapped up in the route map. And, that's kind of it for these two. So we'll look at a third one now. In this scenario, we're going to introduce VPC into the picture. So we'll have 2 firewalls, and they're going to be working in active standby mode, just to show how that works and what difference that might make. And we're also going to do the static routes here, just to kind of go back to a simple design. So the topology looks like this. So here I've put Nexus 4 and 5 into a VPC pair. And then I have one firewall here, it's kind of doing LACP to 4 and 5. And then the standby firewall is connected VPC as well. There's a cable between them. I forgot to put that there, but that's the cable for just the health check for the failover is what's there. And I did move PC2 over to Nexus 3 just to kind of try to separate it a little bit, make it clean. But the PC2 is still in VLAN 192, PC1 is still in VLAN 10. The logical diagram is pretty much the same. So here you have the fabric and the VPC pair connects to the firewall here. The inside network, VLAN 9. So it comes to the fabric, it goes to the VPC pair, into the firewall, to the DMZ. And so as far as traffic flow, now from PC 1 to 2, if we're talking 1 to 2, it's going to come from 1, it's going to go into the primary firewall right now, which is this one, and then it comes back out, and it could use either link, comes back out, and then it goes back to 2. So my drawing's not good, but you see the idea. So they don't talk right to each other, they have to go through the firewall, even though they're on the same switch, because the default gateway for PC2 is the firewall, and PC1 and PC2 are not on the same network. So let's see how this works. And I'd also move to the internet out here to Nexus 5. So, ideally in the real world, you'd maybe make that redundant as well, but we don't need that for our example. So let's look at the key configuration, which is gonna be the same pretty much for one of the first ones we did. The difference is it goes on both 4 and 5. So 4 and 5 both have this static route pointing to the inside interface of the firewall, and default route pointing to the inside interface, and then we're redistributing these static routes. And now on the firewall, this is a port channel now, not a physical interface anymore. So you can bind 2 or more physical interfaces, and then you would go port channel, and I have like port channel 1.9 would be VLAN 9, port channel 1. Or whatever, .192 would be the DMZ. And so that's how that kind of works. And it's for both. These are identical. These have identical configurations. So let's just look at it, see how it works, and test maybe the failover. So here on Nexus 3, just on PC2, that's in VLAN 192, that's interface E14. So E14. It's just in 192, so I had to bring the VLAN 192, show run VLAN. So I brought the VLAN and then put the VN segment and then added it to the NVE interface here. And then 4 and 5 should have the same, VRF configuration. So they're in a VPC pair, so everything has to match. The VLANs, all of that has to match from the VPC video. So here, if you look at tenant 1, there's those 2 routes, but it's on both of them. 2 routes, it's on both of them. And then they're both, if you go look at the BGP, they're both redistributing those. Show run BGP. So they're both, the direct routes was from the layer 3 VNI videos, and then the static route here is these 2 here. So if we look at Nexus 3, show IP route VRF, tenant 1, in order to get to the default route, it knows to use this IP address, which is the secondary IP address on the loopbacks of 4 and 5. And this is just how the VPC works within the fabric. So if if 5 were to go down, this wouldn't change, because that 123 address is on both 4 and 5. That's back to the VPC. And then here's the DMZ. It's being advertised with the next hop of the same thing there, which is a shared IP with 4 and 5. So, and if that way, it doesn't matter which one it goes to, it can get to downstream, if it uses the peer link if it has to. And the firewalls, I think this port channel, I think this one's port channel 3, the first one from the VPC perspective. That's port channel 3, and that's port channel 4. So let's look on like a normal scenario. Let's look at Nexus 3, show BGP L2 VPN eVPN 10.9.0.1. Let's see if it has that. because this would be the MAC address of the firewall's inside interface, this right here, because it's got 10.901. I just looked on Nexus 3. I could have looked on Nexus 4. And so if we were to go to, let's go to 4 and let's see where this is at. You know, I would expect port channel 3. Yep. So the active firewall's on port channel 3. Now the ASA here is using the same MAC address in each VLAN. So you can do that as long as you don't have two MAC addresses in the same VLAN. I think it's just doing that to preserve MAC addresses. So let's also look at it on 5. Okay, so it's also, so port channel 3, which is, they both are agreeing that this one is the active firewall. And let's go to the PC and make sure that it can ping, PC1 can ping PC2. So it can, so they're talking. And then let's make sure PC1 can ping the internet. Okay, that looks good. Now let's fail the firewalls over and see what happens. So let's look at our failover status. So here, this host is primary and it's active. The other host, it detects it, it's secondary, and it's ready. So I'm on the primary right now, and it is saying it is good to go if I want to fail it over. So let's fail it over, and I'll just say no failover active, which will push this to secondary, and it makes the other one active. Okay, so this one's switching to standby. If we switch to the standby, you can see it's active now. Let's go to PC1 and let's quickly see if we can. So the connectivity still works. It's still there for DMZ and for the internet. And now let's go to Nexus 4 and let's see where is it detecting this MAC address. And now we can see that that's changed to port channel 4. So firewall 2 is the active at this moment. Let's take this and run this on 5. That should agree. Okay, so the change, when the firewall fails over, the change happens and it stays, you know, kind of local here to the VPC. The important thing is, like on Nexus 3, if I were to show IP route VRF tenant 1, we looked at this just a second ago, and this did not change. So the default route still has the kind of that Anycast shared IP between 4 and 5. That didn't change. So if we scroll back up, that's the same. That's what was before we failed it over, and this one's after. Didn't change. The change happened here between 4 and 5 downstream. And so that's the good thing is there's not too, you know, if both firewalls are behind a VPC pair, there's not a lot you have to do because to the rest of the fabric, the next hop IP doesn't change. Now there will be something we have to do if there was not a VPC here, and then, you know, we'll look at this next, but if there's a failover event and you're not behind a VPC, that would cause problems that we'll have to fix. But if you're behind a VPC, the next hop IP doesn't change, and that's the key. So that's how this one works. Let's flip it back. I'm curious to see. We'll just flip it back real quick. Let's see if I can see if this will ping, and then I'll fail over just to see how much it drops. So if we go, let me make sure that pings right. Is there a repeat? Okay, let's go back to ASA2. Let's check the failover status. Okay, the secondary is what's active. In the primary, it's ready, so we can fail this back over. So no failover active. Now let's hop to PC1. Oh, it stopped. And I mean, I immediately started the pings, so it's not dropping anything or very little, if anything. So back to the ASA. This one's back to active. Show failover. Ready. If we were to look at Nexus 4, go back here. we're back to our normal case. So that's kind of how this one works, though. Just 4 and 5 have to have the same configuration, and we're doing just static routes redistributing into BGP. So that's how this one works. In this scenario, probably our last scenario, we want to look at firewalls, HA firewall pairs behind different switches, just to see the different behavior. So far, we've looked at firewalls either behind a single switch or a VPC pair of switches, but the behavior, kind of from what the rest of the fabric looks like, the behavior is the same because the two device in the fabric, the next hop IP doesn't change whenever there's a firewall event. And this is going to be one difference of behavior when we separate the firewalls. So let's look at an example and what I mean. So this is the same scenario we looked at earlier, but I just took the VPC down. So I went to Nexus 4 or 5, basically said no feature VPC, and then shut down the peer links. And then made sure Nexus 4 and 5 had the same configuration. So, for example, I had to bring VLAN 66 to Nexus 4. That way it can have reachability to the internet. So you kind of bridge it over. And then here we have, firewall 1 connected to 4 and 2 connected to 5. There's still a link between them, but that's just used for the heartbeat and the replication of state. So let's think about on a normal day. If firewall 1's active, what's the traffic flow? So it's going to be similar to what we've seen. PC1, let's say PC1 wants to talk to 2, it has to go through the firewall. So it comes up here, it goes to the active firewall, and then it goes through the active firewall, which routes it, and then it kind of gets bridged down to PC2. And then the return traffic is the same pattern, just in reverse direction. Now the reason that the Nexus 3 knows where Nexus 4 is because of, we have again, there's our static route, and it's pointing to 10.901, which is the firewall's inside interface. And then this is being redistributed in BGP. So that's how Nexus 3 knows how to reach 4 for the internet and the DMZ. So what would happen now if these got swapped? So this firewall is now the standby, and then this firewall becomes the active. Well, the problem here is that when this firewall fails over, the static route that we have configured here, it doesn't know anything about the firewall states. So this static route remains. What that's going to do is it's going to attract routes to itself. And so, for example, PC1 would come here, and it would still go to 4, even though it should be going to 5. But the reason it's going to 4 is because the static route doesn't have any, interconnecting with the state of the firewall. So they're two separate things. And so when it gets to 4, one of two things could happen. It could just drop it. Worst case, that'd be the worst case scenario. Or Nexus 4 could do another lookup, and then it would bridge it over to 5, which would then make it to its destination. But this traffic pattern, like a big M, is not what we want. And so what we may think is just put the static route on both and point it to 10.901. So the static route is on both, it's being redistributed on both. But the problem with that is, even on a normal case where the firewalls aren't switched over, Nexus 3 has an equal cost to either one. Sometimes it would take the right path, sometimes it could take this path, and then it would have to get switched back over or routed back over here to 4. So even on a normal day where the firewalls aren't swapped over, if you put the static route on both, you'll have the standby attracting traffic that is just going to have to either drop or bridge to the right place. So that's the problem. And there's a couple fixes. There's 2 main fixes at least. And let's just look at the config for those, which would be this. So one of them you just put on Nexus 4 and 5. What we're basically doing here, a while ago I said The problem is we have static routes that have no knowledge about the firewall state. And here we're going to try to kind of bring those together by doing a tracked route. So what we're going to do is track 10901, and we're going to use the HMM process. The HMM process is the normal process where a VTEP or a switch, when it learns a MAC address and then it creates a BGP update for it, that's the HMM process. In other words, a device, a Nexus switch, is learning something locally. And so what we're saying is whenever you learn 10901 locally, I want you to install these routes in the routing table. These two routes. If you're not learning this locally, pull the routes. So here we're making a sort of a dynamic, route tracking thing where if I'm learning 10901, which is the inside of the firewall, if I'm learning that locally, install these routes. Else, don't. If I learn this over BGP, don't install the routes. That means I don't own it. Now this is one fix. And then the other fix, you could do this, which these are separate fixes on all of the switches. You could just put this route 192.168.10/24 to 10901, and then we would basically let the BGP update process tell us where 10901 is. So every time there's a firewall change, the next hop for 10901 will change. And we'll look at both of these. So I actually do want to lab this one up and try to look at both of these. I haven't labbed this up yet. So let's lab this up and see how this works. I'm going to see first if we can recreate the problem. So I don't have anything configured yet. So let's go put the static routes and redistribution on 4. And because right now Nexus 3 shouldn't have a route there. Let's verify that. So show IP route VRF tenant 1. So we have no default route and no route to the 192.168.1. So let's go to Nexus 4. Let's go into the VRF. And let's put the static routes. So let's do 192. And then the default route. Then we need to go to BGP and redistribute them so that Nexus 3 can learn about it. Go under our tenant section because that's what we're trying to modify. Under IPv4, because these are going to come across as type 5 routes, what we redistribute. And then let's redistribute our static routes, and then we have to use a route map. RM permits everything. And then to get our default route, we have to put default information originate, or otherwise the default route doesn't go without this command. So let's go back to 3 and see at least if this tenant has reachability now. Okay, so there's our default route. And the next hop is Nexus 4, 151.4.4. And then here's the DMZ, and it has a next hop of 4.4. So looks good. Looks like what we would expect. So let's actually see if this works or if we need to do some more. I'm not sure. So let's try to have PC1, which is on the inside, ping PC2, which is the DMZ. Okay, so that looks like that was enough to make it work. So we have, this is a normal day. We have the routes on 4. Let's test the internet connectivity. Firewalls are in the normal state. So that looks good. Now let's simulate the problem. So I'm going to fail the firewalls over now. So I'm just going to go to firewall 1. Let's check the state, make sure it looks good. So primary active, that's what I'm on, and it's ready. It says standby ready. So no failover active. We'll flip the roles. So now this one is standby. And this one is active, just so I can keep it straight. All right, now let's go to 3 and let's look at this table again. Let's see what changed, what didn't change. And so there's the default route again. But notice it's still going to 4. Because that route we're redistributing, it's still there. And so it's making our default traffic go to 4, and then it's making our DMZ traffic go to 4. But the active firewall is on 5. So here's the disconnect between the route and the firewall states. So now, does that cause a problem? Let's see. Let's see if I can ping the DMZ. Okay, so here TTL expired in transit. So it looks like there could be a loop or something here. So this just not working at all. And let's try the internet. It's the same thing. So we do know Nexus 3 is sending it to 4. And then let's see if we can see what 4 is doing with it. So here it's trying to send it to 10.901. And 10.901 is reachable over 5. So it looks like it's trying to send it to 5. And so we're going from, PC1, Nexus 3 going to 4, which is wrong. But 4, it looks like it might be trying to send it to 5. Let's see what 5 is doing. So 5, if we're trying to go to the DMZ, it's sending it back to 4. So this is the loop that we're seeing here, because this is being learned from, we're distributing from Nexus 4. And so 4 is telling 5 to get to this network, come to me. So we've made a loop here. So that's one problem with this design. So the obvious thing, you might think is, let's just go put the static route and the redistribution on 5. And let's do that. So I'm just going to copy what we have on 4 and put it on 5. This will fix a little bit of it, but like I was saying a while ago, even on a normal day where the firewalls are in normal states, we'll still have that suboptimal connectivity. Maybe I'll show you what I mean here. Okay, so now we need to go to BGP and do the redistribution here as well. So here we redistribute our static routes with that route map, and then we do default information originate to let the default route go. Okay, now let's look at Nexus 3, see if that did anything different at all. So it's still sending it to 4, which is wrong. So even when we put these routes here, it didn't really fix our problem. So it's sending them to 4. And so let's go to PC1. Let's see if that made a difference though. Okay, so it looks like the traffic is working at least, even though it's taking the suboptimal way. In other words, whenever we do the lookup on 3, how do I get to the DMZ computer? It's sending me to 4. Now if we go ask 4 how it's getting there, we're just tracing this hop by hop. It's saying, well, it knows it needs to VXLAN encapsulate it. And that should, I think I meant to put 10 as where I want to send it. 10.902, it knows it needs to encapsulate it. Let's look at the BGP for 10.901. So here it's sending it to 5. And so we have that kind of that weird traffic flow where it goes to 1, it's going to the wrong place, but then 4 is sending it to the right place. And then it can make its way back. So this pattern is what we want to avoid. Even though it works, it's just suboptimal. And this is the best case scenario. Worst case would be it would drop half of the traffic. So if Nexus 3 went to 5, it would work. If Nexus 3 ever chose 4, it wouldn't work. That'd be the worst case. So let's put these fixes in. Let's try one of these fixes so we can have a better, a more optimal traffic flow. So the first one that we looked at was we want to track the route through the HMM process. That way these routes will only be installed when Nexus 4 or Nexus 5 is learning them locally. So let's start with 4, just since I'm on it. So we're going to create a track object. I'll just call it 5. We're going to track this IP address, which is the inside interface of the firewall. So in other words, we're going to say, I want to know if the inside interface of the firewall is connected to me. If it is, we're going to do something. If it isn't, we're going to do something as well. And then we're going to use the reachability HMM process to do that. And then it takes us into this sub mode where we have to specify what VRF are we making this for. Now that we have the track created, we need to put it on the route. So we already have the routes made, but we need to put this at the end of them. Okay, so let's go to the end of this and just put track 5. Same thing for this. All right, and now we need to do the same thing on Nexus 5. So I'm just going to copy what we made and put it on 5. And then attach it to the route. Okay, now we should be able to view the status, I think. Show track, maybe. Okay, so, okay, good. Track is up on 5. I actually expect it to be down on 4. And if that's true, then it's working like we think. Okay, good. So here, this should be working here like we were expecting. So what we're saying, this is down on 4 because 4 is not learning about 10.9.01 locally. So we can... So show BGP L2 VPN VPN 10.9.01. It's learning about that from, you know, its next hop is 5. So it knows 10.9.01 is not on itself. On Nexus 5, here we are learning it through that HMM process. So the reachability is up here. And when the reachability is up, what it's going to do is install this route in the routing table. And when it's down, when the track is down, it's going to pull these routes. So in other words, they should be pulled from Nexus 4 right now, because right now it's the standby, and this firewall is the active one. So it should be installed here. Let's go to 3. Let's look in the routing table of the tenant. And now we can see to get to the default route, it's going to 5. And again, it's still flipped over. So this is the standby right now, and this is the active. And we're going to the right place now. We're going directly to 5 because 5 is installing those routes. So let's test our connectivity. That looks good. And then we'll test our internet. Good. Okay, now that we've got the configuration in there, let's flip the firewalls over and then test it here. So I'm going to go here. This is the active firewall right now. Let's flip it back over. No failover active. What this should do is the track status should flip. So now Nexus 4 should be learning show track. So now the reachability on 4 is up, and then 5 should be going down. So when I flipped the firewall over, the firewall 1 took over 10.9.01. And then when Nexus 4 learned that triggered the track, which installed the routes. And then when it sent a BGP update, 5 got it, it realized, oh, I'm not learning 10901 from myself anymore. I'm learning it from somebody else. So the track object goes false and it pulls the routes. So that's how that works. That's the first fix you could do. You could just put that on 4 and 5. So let me clear that because now they're back in the normal state. Now the other thing you could do, the other fix for this, is just to put a static route on all the leaf switches here, including 4 and 5. So let's wipe our let's wipe this configuration here. Let's just to get these back to where it was kind of before, and let's just look at this other fix because it's really quick. IP route. So actually we're gonna just take the track off. Well, let's see. Let me just take the whole thing off and then we'll put it back on without the track. Okay, let's check this out because this is what we want to put everywhere. These two routes. So one for the internet and one for the only DMZ we have, but we're pointing it to 10901. And then we're going to rely on BGP to tell us where 10901 is. Now I don't need any redistribution here or anything. So let's take that out of 4 and 5 is the only place we have that. So let's take out that redistribute the static, and let's take out default information originate. That direct we can leave because that's not even doing much for our purposes here. That's just advertising the SVIs for external connectivity, which we're not even using right here really. So what I'm doing here is taking the redistributions out, just because we're just going to use two static routes on each switch. All right, so we're back to where we should really have no connectivity from Nexus 3's point of view because it doesn't have the routes yet. So show IP route. See, it has no default route and no route to the DMZ. So on 4. I put the routes on 4 and 5. We just need to copy them to every other switch, which is only switch 3 in our case. Net 1 and 2 don't need them because they're not processing hosts. They're just part of the underlay. So here we want to take these 2 routes, and I'm just going to copy this into Nexus 3. Okay, now if we look at the routing table on Nexus 3, we have the default route here. Now let's see if that's enough though to give us connectivity. And it is. And let's test the internet. Okay, that's good too. So again, all we've done on 3, 4, and 5 is just put these 2 static routes. Let me look at another one. We put that on all of the leaf switches. There's no redistribution going on anywhere or no tracks going on. Now how it's working is it tries to send traffic to 10901. So let's look at this and then cause a fail over here. So let's look for specifically, actually let's just look for, okay, so the default route is being learned. There's the static route. Let's do, how do I get to 10901? 10901. And so here it's sending it to 4 right now. Now it's sending it to 4 because 4 is advertising 10.9.01. So if I look at BGP 10.9.01, my next hop is 4. So basically what's going to happen is if we fail the firewall over, what I have highlighted here will change to 5. We don't have to mess with any static routes or anything once they're in there. So let's simulate this. So this should be the active. Standby is ready. No failover. Active. So when I hit this, firewall 2 is going to take over 10.9.01. Nexus 5 will learn that and send a BGP update, which will cause, for example, 3 to flip who that's going to. So let's no failover active. If I go back to 3 and refresh this, you can see what I have highlighted actually now changed to 5. So that's how this one works. We're just relying on BGP to change the next hop to where whoever has 10.9.01. So you could, solve the problem we were seeing 2 different ways. The first one is just configuring the tracked routes here, or you could put the static routes on every single host and point it to 10.9.01, and then we'll rely on BGP to tell us where 10.9.01 is. All right, so you can see it's a little more to think about when they're not behind a single switch or a VPC, because the next hop is essentially going to change, like from Nexus 3's perspective, whenever they're not behind the same device, and that's what we have to deal with when they're behind different VTEPs. So I think that's all for this. Just wanted to show how that works and the couple fixes, at least 2 fixes for it.